Hi everyone, let's talk about the theorem on friends and strangers in graph theory. Let's suppose we have at least 6 people at a party. So assume that there are at least 6 people and pick any 6 of them. And then we're going to classify relationships between pairs of them. So if they have met before, call them friends. If 2 of them have met before, or you can call them acquaintances because they might not necessarily be friends, but we'll be using the word friends. And secondly, if they have not met before, call them strangers. So we're going to use the color blue for friends and the color red for strangers. And you'll see how this is graphically represented in just a moment, literally as a graph. The theorem states that there exists 3 people who are pairwise friends, or 3 people who are pairwise strangers. So you're either going to get as a graph a triangle of friends or a triangle of strangers. And we'll prove that now. So what we're going to do is that we're going to represent the people as the vertices of a regular hexagon. 1, 2, 3, 4, 5, 6. And we're going to draw a blue line between 2 of them if they're friends, and a red line between them if they're strangers. So there's going to be 6 choose 2, however many that is, line segments between unordered pairs. Now, the idea behind the proof is to pick any particular person or vertex and to draw or consider the 5 relationships that this person has with these 5 people. And if you know the pigeonhole principle, you don't have to use the pigeonhole principle, but if you don't use the pigeonhole principle, you have to use some casework. But the idea is that we have 5 relationships mapping to 2 colors. We don't know what they are, the 5 colors that we're going to be drawing, but the strong pigeonhole principle tells us that there's 5 over 2 ceiling function equals to 3. 3 of these relationships that are the same color. So let's say that those 3 are this one, this blue one, this one, and this one. So let's say they're blue just for argument's sake. They could be red. So the idea now is to consider if we call these the other endpoints A, B, and C, the idea is to connect those ones. And so we get a triangle now, and they might not be red. I'm just drawing them to be red for argument's sake. But if A, B, C, so AB, BC, and CA are all strangers, we are done. But if any one of them is blue, so we have blue here, then we get a blue triangle because of V, A, and C, or V, A, and B, or V, B, and C. So that's the way this casework is completed. We either have ABC is a monochromatic triangle, meaning they're all the edges are the same color, or we find that one of the two original edges out of these three has a third edge that has the same color as it. So that proves the theorem on friends and strangers. Thanks for watching, and I'll see you next time.